So, forces and laws of motion. So, at the end of this lesson, the students will be able to differentiate contact and non-contact forces and also properties of static and kinetic friction, apply acquired competencies to the laws of motion and forces in problems and technical solutions, and analyze the effects of friction on moving objects. So, before we differentiate those types or these types of forces, so we are going to introduce first dynamics. Okay, so we'll be dealing with forces and motion, meaning what causes the motion of the object. So in the previous lesson, we had description only of the motion. So how far has the object moved? How fast does it move? Okay. Um, how long does it reach a certain point? So the reason of these motion examples were not considered in the previous lesson. So now we're going to try to analyze what are the causes of the motion. So we have here some examples. Okay, so the reason why the roads are um there's a banking angle on the road. So why is it designed that way? Why do accidents happen for poorly designed roads and stuff like that? And also for the motion of people, no, jumping, walking, running. So what causes this motion? So we're going to um, discover, okay, the application, real life application of these causes of motion using Isaac Newton's laws of motion, which is the foundation of classical mechanics. So let's begin with the definition of force. So it's either a push or a pull. So we use the capital letter F to denote this vector, no, quantity. So since it's a vector quantity, so it has both magnitude and direction. So its as a unit is newtons from, of course, the person, Isaac Newton. So its abbreviation is capital letter N. So 1 Newton is equal to 1 kilogram meter per second squared. So this unit of force is somehow related to mass because there's a kilogram here, to displacement, to time, or to velocity, or to acceleration. Okay, so it's related to our kinematic quantities in the previous lesson. So we'll be combining lessons 1 and 2 and the Newton's laws of motion to know what is the effect of the forces on the motion of the objects. So we have types of forces, okay, based on the interaction and the type of interaction between these objects. So we have contact and field forces. So for contact forces, from the term itself, contact, so it involves physical contact between two objects. So below are some examples. So the hand is touching the handle of the spring. So if you pull the spring, so it would be easier to do that because you are touching the handle. So another example, if you are pulling, okay, this cart, or if you are kicking a football. So the second type wherein no physical contact is required, okay? So it acts through empty space. So it's a field force or a non-contact force. So this is an example of this type of force. You know that there's something happening between the iron and a magnet. Okay, so that's because of the field force. Okay, so another example of field force is the gravitational force. So of course, if, for example, this apple will fall to the ground, so we cannot see, okay, a physical contact no, between the apple and that thing that is pulling, no, the apple. Okay. So the electromagnetic force is also another example. The weak forces in radioactive processes are forces, no, in nuclear chemistry. Okay. So these are field forces. So these three are in micro scale. No, they are um, dealing with subatomic particles. So for this part of our discussion, so we'll be focusing on the gravitational force and, of course, the contact forces, the push and the pull. So since force is a vector quantity, so of course, no, it has magnitude, no, both magnitude and direction. So if you are given more than two forces, so we're going to use what we learned in lesson one. Okay, so use the rules for vector addition to find the net force acting on an object. So in this figure, so we have here two forces acting on this scale, and they are applied perpendicularly to each other. Okay, so we can solve for the resultant force by getting, no, the hypotenuse of this right triangle formed using the two arrows, okay, representing the two forces. So on the figure is a scale. So if you increase the force you are putting, no, on the scale, so of course the reading will increase. Okay, because the magnitude already is increased. So the magnitude, take note, it tells us only of the amount and not the direction. So for forces, so how much or how hard the force pushes or pulls. So magnitude of force is having, of course, the unit, no, newtons. Again, abbreviated using capital letter N. So now we go to the laws of motion. So according to Newton's first law, so when no net external force acts on an object, okay, so the object either remains at rest or moves with constant velocity in a straight line. So meaning the acceleration is zero. So if there's no net external force, so take note that only the external forces are considered. So the nuclear forces or the electromagnetic forces are not considered. Okay, so only the external, so outside forces. Okay, so the push, the pull, and the gravitational force. So external force. Take note of that. Okay, so net external, no? When I say net, so it's the summation. Okay, so vector sum of all external forces exerted on the object. So if the object is initially at rest, so it remains at rest. If it is initially in motion, then it will continue in motion with constant velocity. So there's a condition, no, with constant velocity. So if there is already a net external force or also called unbalanced force, then the motion of the object will change. It will be siguro moving, no, but no uh no longer at constant velocity. Okay, so there will be acceleration or deceleration depending on the motion. So once the object has been set in motion, so no net external force is needed to keep it moving. Okay. So for the constant velocity condition, so we call this observation Newton's first law of motion. So it's related to the inertia of an object. Okay. So that's why um, for it to be kept moving. Okay. So moving na at constant velocity. So there should be no net external force because of this explanation, the tendency of an object to continue in its original state of motion. So it's because of what we call inertia. Okay, so that's why this first law of motion is called law of inertia. So mass and inertia are related. Okay, So as you can see here in the picture, so there's a man and a child. So between the two, okay, obviously, the child accelerated more compared to the man, okay, because of their difference in their masses. So mass, that's because of the composition of our body, what atoms are found in our bodies. If we are going to weigh all those atoms, all those molecules, so you'll get, okay, the mass, of the object. So for inertia, again, it's a tendency of an object to continue in its original state of motion. So if the object has more mass, okay, so the harder it is to change its motion, meaning the more inertia it has. Okay, so between the two, okay, so the um, child has a lesser inertia, okay, because she has a lesser mass. Take note, okay, it's not weight, no, it's technically called mass. If we are using the kilograms na unit, okay, so it will become a force if we are going to multiply that with acceleration due to gravity. So it's already a force unit, no, in newtons. But sometimes, of course, we interchange, okay, these concepts are not interchanged. No, we usually use the term weight, pero atong gimin is the mass, no, which is usually in kilograms or in pounds. So we have what we call inertia of rest. So for example, if you're riding a roller coaster, so if you have reached the maximum height, okay, so meaning the velocity there, no, is zero. So to keep the roller coaster moving, so there must be a force acting, okay, or not continue moving, okay, race. So at zero velocity at maximum height, okay, so because of gravity, no, and other forces that are acting on the roller coaster, so of course the track is going downward na, diba? So there is already a change in the motion. So there must be a net external force acting, okay, on the cart of the roller coaster. So since there's a sudden change in the velocity, no, in the motion of the roller coaster, so tendency is, okay, initially it's at rest. So once the roller coaster will move downward, so the persons riding, okay, will tend to move their bodies backward, back to the original, okay, original position, okay, or direction, which is at the highest point. Okay. So we tend to move backward rather than forward. So this is due to the inertia of motion. We try to maintain our position of rest. So it's different with the inertia of motion. Okay, so the object is already moving. No, so for example, if you're riding a car and you suddenly stop, okay, so if you're not wearing a seat belt, so tendency is, okay, so you will be moving forward even if the car has already stopped. Okay, because that is your initial state. No, you are moving forward, but then the car suddenly stops. So you continue to move forward for maybe a split second or milliseconds. Okay, so if you do not have a safety device, no, such as the seat belt or an airbag, so wala, no? So mulusot sa windshield, what do you call that part of a vehicle? So that's for inertia, okay, of motion. So to know more about how seat belts are designed, so you can visit this YouTube video. So The second law of motion is about acceleration. Okay, so according to this law, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. So mathematically, it's this equation. Okay, so acceleration is directly proportional to the net force. So net force meaning summation of the forces. So there are arrows because they are vector quantities. Now acceleration is also a vector quantity. Okay, but acceleration is the inversely proportional to mass. Or if we arrange the terms and make it into, or not the terms, no, the quantities and make it into an equation, okay, sorry. So this is already the final equation, and I think this is the more familiar na an equation. So net force is equal to the product of the mass and the acceleration of the object. And sometimes omit the subscript net. Basta take note na it's a summation of forces, na it's a net force. External force, to be specific. Okay, so since again, force and acceleration are vectors, so they have x and y components, okay, for two-dimensional no motion. So if we have force acting or a net force acting along the x-axis, so its effect is on the acceleration no, along the x-axis. Okay. And for the motion along the y-axis, so the net force along the y-axis will be the reason no, why the acceleration has reached that value along the y-axis. So you need to solve separately, okay, the x and the y components and just use the resultant no, of the components to solve for the magnitude of the net force, okay, or maybe the acceleration no, is required. So same, okay, same process. So get the x component and y component of the acceleration and then get the magnitude, okay, of the resultant of the x and the y components. Okay, and of course for the direction, no, so we use the arctangent from what we learned in lesson 1. So again, for y component, so we need only the net force along the y-axis for the acceleration. Okay, so by the way, the equation on law of acceleration is derived from a momentum rate of change, no time rate of change. So momentum shall be discussed in another lesson. But just to show the derivation, how we came up with net force is equal to mass times acceleration. So it's because of the net force being equal to the change in momentum, okay, with respect to time. So momentum is the product no, of mass and velocity. Okay, so derivative of mass times velocity. But since we are focusing on one object, so basically the mass is constant. So we can put the m before the dv. Okay, we have that property no in derivatives. Now we can put the mass or any constant okay, before the derivative. So we have this equation mass times the change no, in velocity with respect to time. Or this fraction here is the acceleration, okay, of the object. So net force therefore is equal to mass times acceleration. So for convenience, so sometimes no, omit, okay, remove the arrows. But take note that force and acceleration are vector quantities. Okay, so here are some applications. So if you have an empty shopping cart, of course, it accelerates more compared to this full cart. Okay, assuming that the person applies the same amount of force on the two carts. And another is this one. Okay, so they can break this slab of bricks by moving their hand no swiftly. So dapat greater acceleration so that greater amount of force will be exerted on the bricks. Okay. So enough for the bricks to be broken. So we have this special type of force called the gravitational force, obviously, because of gravity. So you can put a letter G denoting no, na it's because of gravity. Okay. So according to Newton's second law, so force is equal to mass times acceleration. So since acceleration here is due to gravity, so what we get is the gravitational force. So it's just the same as F equals m times A, where A is acceleration due to gravity. All right. So we have the convention no, in lesson 2 na because of gravity. So it's the object no, is pulled by gravity. So it is directed no, toward the center of the earth. So the acceleration due to gravity is directed toward the center of the earth. Okay. So the force, therefore, is also directed toward the center of the earth. And the magnitude of this gravitational force is what we call the weight, okay, of the object. So if just disregard the sign, okay, convention or the direction, and we focus on just the magnitude, so what we get is the weight of the object. Okay. So from this law of acceleration equation, okay, so if we are going to get lang the magnitude of the gravitational force, so its weight no is equal to mass times acceleration due to gravity without minding no the sign for G. Okay, but later on when we will be using no weight for problem solving, then since it's directed downward, so we'll be using a negative okay value. For now, this is just the magnitude of the gravitational force. So just use positive 9.81 meters per second squared. Okay, so for example, if the mass of an object is 50 kilograms, then its weight is 490.5 newtons because 50 times 9.81 is 490.5. So kilograms for the unit of mass, meters per second squared for the unit of acceleration. So kilogram meter per second squared is newton. So 490.5 newtons. Okay, so take note again that mass is just the amount of matter in an object. So technically, okay, if you're asked for your weight, so supposedly your answer should be in newtons. But since we are having the same acceleration to gravity, okay, naarama to sa Earth, so manang accepted na weight, no? If you're asked for your weight, you say 50 kilograms. Okay, but technically it should be in newtons. Or if you are um, giving no a number in or a quantity in kilograms, so that should be the mass and not the weight. Okay, so the third law of motion is about action no, and reaction. So it states that when two bodies interact, they apply forces to one another that are equal in magnitude and opposite in direction. So forces are applied to another object. Okay, it's not lang one object with a lot of forces acting on it. Okay, so these two forces must be equal in magnitude but opposite in direction. Okay, so for every action, there is an interaction. So therefore, forces, they act by pair. Okay, so walay mag-solo na force. So sana all force bitaw. So a pair of forces acting on two interacting objects. Okay, so equal in magnitude but opposite in direction. So for example, if you're pushing on a wall, so the wall also pushes on you. Okay, so of course, no, if the forces are balanced, so man siyang we do not balance, okay, opposite direction but same magnitude. So we cannot feel, of course, no, that the wall is pushing on us. But of course, we have applications of this third law. Okay. So, for example, in walking, okay, we cannot walk if we are not pushing, okay, on the ground or on the floor. So, our force exerted, okay, on the ground is balanced, no, by the force that the ground act, is acting, no, on us. So the ground pushes forward and up on the runner because it's the opposite direction. So equal in magnitude but opposite direction. Okay, so when you run or when you walk, so you need to push on the ground so that the ground will also do the same thing, no, push on you para you can move forward. So if there's no reaction force, so meaning no, your foot will be below na the ground or will sink na to the ground because wala mo counter, 'di ba? So similarly, if the action force applied by the foot of the person is significantly higher, so the magnitude, okay, of the force that the ground will push on you will be greater. So mas dako ang force nga mahatag sa imo so manang reason na you can jump na. Okay, so the higher the amount of force, okay, that you placed on the ground, so the higher amount of force that the ground will exert on you. So mas mo accelerate ka no and you will go um at an extended no nga distance. Okay, so meaning pwede na ka mo jump. Okay, so kana because of action and reaction forces. So another example is for a balloon, okay, such as hot air balloon. So why does it move upward? Okay, so when air is released with its end untied, okay, so siya a balloon filled with air when released with its end untied lets out air with force. Okay, for hot air or for hot air balloons, so the difference in the temperature no inside the balloon and outside, okay, cause the movement of the air molecules. No? So there's a change in kinetic energy. So meaning there is pressure, therefore there is force, okay, supplied by the air. So with the help of the action force that is caused due to the air rushing out of the balloon, okay, with the difference in again temperature or the pressure in the atmosphere and the pressure inside the balloon, so a reaction force gets developed that causes the balloon to move forward. So same concept with rockets. Okay, so the rocket will move upward, okay, because the force on the rocket is the reaction of the force on the gases. So hot gas comes out of the nozzle. Okay, so there's a force downward. So reaction would be a force upward, no, in the opposite direction. So causing the rocket to move upward. Okay. So when we solve problems involving forces, so we construct no a what we call free body diagram. Okay. So just don't mind first the values here. So for a free body diagram, so free body, okay, so we just use lines and points here. We do not draw the objects. Okay, just the possession of the object and the forces, no, the arrows representing forces that are acting on the object. So it's very important to use what we call FBD, okay, free body diagrams. So sketching all the forces acting on an object. Okay, so for example, no, so two people are pushing a 1,000 kilogram car. So this is a 1,000 kilogram car, and these are the two persons. Okay, So the first person exerts a force 275 newtons, for example. So this person, 275 newtons east. Okay, while the second person exerts 395 newtons also east. So there is an opposing force, okay, labeled lowercase f. Okay, so you cannot see that in the picture, okay, but you can draw that no, on a free body diagram. So these two forces, the 275 newtons and 395 newtons, are going no eastward. So when you make a free body diagram, so this circle here represents the car. So those two forces are drawn from the car, okay, and then towards the direction of the application of the force. So this is the 275 newtons, and this one, the second blue arrow, is the 395 newtons. Okay, so you can uh, put this first force on top of the second force. Okay, but for emphasis, there are two forces. That's why wala lang along the x-axis, no, ang first force. Okay, but both are going to the right or going eastward. Okay, then the opposing force mentioned is 560 newtons west. That's why it's called opposing, no, because the direction is opposite already. So this arrow, red arrow, represents the opposing force. It goes westward with this magnitude. Okay, that's why the arrow is longer, because 560 newtons is greater than 395, and of course now the 275 newtons. Then arrows are drawn, okay, again on the horizontal axis and also along the y-axis. Okay, so there is the gravitational force, or the magnitude, no, it's the weight. So it's a downward force. It's always directed downward. Okay, because we kind of know the acceleration is directed towards the center of the earth. So weight is for a straight line motion, no, or for any type of motion. If you put an inclined plane, it's always directed downward. Okay, and this one, okay, is what we call a normal force, which will be explained later. Okay, so letter N means normal. Okay, so we have the weight and the normal force along the y-axis. So if the object will not move along the y-axis, then there must be a no net external force, meaning the object will remain at rest along the y-axis. Okay, so if both normal force and weight have the same magnitude, but they are in opposite directions, no, so no net external force, so it will not move, okay, or accelerate, no, along the y-axis. But since we have different magnitudes of the forces along the x-axis, so there must be a movement, no, along the x-axis, because there is a net, no, external force, or what we call unbalanced force. Okay, so when we write, no, the forces along the x-axis, okay, so we get the sum. Okay, just like in lesson number 1. Okay, so the x components, no, of all the what do you call this, all the vector quantities in that particular problem. So you get the summation. Okay, and then to do away with cosine theta, okay, since it's always, okay, for this type of motion, it's always either east or west. So instead of using an angle, okay, it would be easier if we are going to put the negative sign ourselves. Now, if we are having the west direction as the negative value, then we put a negative a negative sign here, meaning the operation becomes subtraction. Okay, and for the blue arrows, so they are positive because they are going to the eastern, no, direction. Okay, so again, in lesson one, no, it's always an addition operation, meaning plus, no, so many terms with plus signs between them. Okay, so if we are putting, no, the angle in standard position using sine and cosine components. Okay, pero para mas simple, so kitay mo assign as any negative. And same with the net force along the y-axis. Okay, so we have only two arrows, so we add up, okay, the normal force and the weight. Okay, with kato, no, taking note which of the two is negative. So weight is directed downward, so it must carry, no, a negative sign. Okay, later, no, for the computation. So this is what we call superposition of forces. Okay, so the effect of the summation of the forces, okay, have the same effect as a single force equal to the vector sum of the forces. Okay, so it's called superposition. So ang totality of the forces, sa may effect niya on the object. Okay, so it's as if there's only one force acting on the object, but in reality, no, more than one, yun na. Even along the y-axis, no, the object is not moving. Okay, there's at least two forces acting, no, on the object. Okay, so we add up all the components along the x and along the y-axis. Okay, so we'll be having computations, no, later after we discuss all the concepts in the introduction, no, to dynamics. So what causes, no, the motion of the object. So the second type of force that we'll be dealing with, okay, is the normal force as introduced earlier. Okay, the one with the subscript na capital letter N. So N here is not the unit half or force, but it's the type of force known as the normal force. So some are using lowercase n. Okay, so it's the normal force. So it's defined as the force that any surface exerts on any other object. So it is a contact force. No, the surfaces of the two objects must come in contact. And it's always perpendicular to the surface. So for a body resting on a horizontal surface, the normal force is vertical and is equal to the weight of the object. So assuming that there are no forces applied, okay, to the object along the y-axis, it's not pushed up, upward, or downward. So only the weight and what we call the normal force. So the two must be equal. Okay, for a body resting. So it's not moving. So acceleration is zero, no? Meaning there's no net external force. So it must be that the normal force and the weight are of the same magnitude but opposite directions. So for an inclined surface, so the normal force now is not vertical and not equal to the weight of the object. Okay, just like in this figure. So weight is always directed, no, downward towards the center of the earth. Okay, but this time since the surface is already inclined, so according to the definition, normal force is always perpendicular to the surface. So if the surface is inclined, so the normal force will be rotated na. Okay, so that it will be perpendicular with the surface. Okay, so this is the normal force, no? And depending on what surfaces are in contact, if they are considered to be with friction or without friction, so it depends on the given problems. For this one, there is an opposing force, not to the motion. So using lowercase f. Okay, so it must be that the surfaces that are in contact, no, are not frictionless. Okay. So you can safely assume na the surfaces are frictionless unless it's stated no na there's static friction and kinetic friction. So similar to lesson 2, we have different assumptions. Okay, you cannot always use these equations, no? So you must follow the conditions, bale. Okay, so objects can be modeled as particles, and we are interested only again, as explained earlier, no? External forces only acting on the object. Okay, and we can neglect reaction forces because we'll be drawing a lot of arrows if we are going to include no the reaction forces. And in the free body diagram, no, the middle, it's the object that the forces are acting on. Okay. If you will be drawing the reaction forces, so it's actually a separate free body diagram, because it's now being acted on. Okay. Another object. So two different free body diagrams for action and reaction forces. So we'll be focusing on just one object. No? What is the effect of the summation of the external forces on that object? So we neglect no, the reaction forces. So we initially we'll be dealing no, with frictionless surfaces. So if it's not mentioned, okay, what is the coefficient of friction in the problem, then we assume that the surfaces are frictionless. Okay? And masses of strings or ropes are initially negligible. So these are the assumptions, and that the force that a rope or string or cable exerts is away from the object and parallel to the rope. So if you have okay the example no in the contact forces. Okay. So if you're pulling no on a cable or a rope, so that rope must be attached to the object that you are pulling. Okay. And that magnitude of the force is what we call the tension, okay, in the rope. So we have what we call no particles in equilibrium. So equilibrium, no, there's something that is equal no, to another quantity. So from the law of acceleration equation, okay, so if the particles are in equilibrium, okay, the forces are in equilibrium, or the object is in equilibrium, meaning there is a balanced no force, meaning there's no net external force. Therefore, acceleration is zero. So if acceleration is zero, then you have a net force equal to zero. Okay, so if along the x-axis, nga equilibrium siya, then F sub net, okay, along the x-axis is zero and also at the y-axis. So not moving ang object, or it can be moving but at constant velocity. Okay, so these are the components. No? Both are zero. So we'll be talking about particles in equilibrium in the sample problems. Okay, so the application of the law of acceleration equation and the different concepts in dynamics. Okay, so refer to the next video no, for the examples. All right.